Questions, please. Water flows through a tube of diameter 25 mm with an average velocity of 1 meters per second. The properties of water are given. Prandtl number. Using Nusselt number is equal to 0.23. Reynolds number is equal to 0.8. Prandtl number raised to 0.4. The convective heat transfer coefficient is. You don't have to remember anything. Everything is given there. You have to remember what is Nusselt number. That's don't have to write the question. Say it is 2014, 2000. This is 2014. This is pipe flow. I have not done pipe flow till now. I have to do next. But still, you can do it. That's what I'm saying. Okay. So you can guess things and you can do it. Set 4. Even something comes which you have not done also. It's a pretty easy to do. I think done. Questions are done. All are repeat questions. Okay, let it be repeat question and we will do some more. Okay. There has been question like ratio of momentum diffusivity to thermal diffusivity is Prandtl number, Nusselt number, Biot number, Lewis number. This question has come in 2015. We're done, students. I think I have to go to the next topic now. The questions are done. I have to go to pipe flow direct. But tomorrow I'll complete pipe flow and natural convection and problems also. But tomorrow we will complete the. Will not do any derivation here. So today only I'll start with pipe. When the students come, I'll start with pipe first. No more questions. Other questions are the ones which you can do. So I'll not worry about it. Even if it's half an hour, it's half an hour is very useful. Is it not?
Is it 110?
Let's see. Answer is 4613.
Sir,
Yes, please.
how was it?
Bus. ಅಷ್ಟು ಕಾಲೇಜ್ ಅವಚನ ಇಲ್ವಾ Atena ka tu ang bai sang etra bai to yan sa shi no etra etra onge much dog you know just
Yes.
Nihal, I was able to start. I'll start now, new topic. I thought of calling you saying that You said the only problems you are doing, sir, problems are done. There's no more problems there. And whatever problems are there are on Prandtl number, which is repetition. So we'll start with only one. This is actually from pipe flows only, but you can do it. Come here. Go there, go there, go there. Don't worry. Once he clears, yes, yes, yes. Once you clear, you go. This time, just clearing is important, Shane. Okay. Yeah. 2900. Allah. Wrong. It's not 2009. He's saying the answer is 2900. It is not the answer. Oh, you're telling the year, is it 2014? I'm sorry. You're telling the year, you're telling the answer. Okay. Water flows through a tube. Now it is similar. It's tube flow. I agree. But the Nusselt number is given. When you say Reynolds number is 0.3, 0.8, it is turbulent flow. Okay, that keep in mind. It's not laminar flow. And you see PR raised to zero point 0.4 means it goes with the turbulent flow. Huh? Power of Reynolds number. We are not worried about what is Reynolds number. What is that you got here? You got less? Whatever be the case, okay, what is Reynolds number? Reynolds number is, uh, I'm not sure about this. Let us see it. Okay, what he said is right. So velocity is 1 into,
That I got 34,004 KT2.
ah, yeah, 34,000 something. So that is my guess that this is a double. What? Reynolds number. Ah, yes. Correct. So it's a turbulent flow. In pipes, it's a turbulent flow. RE is, you know what is RE in turbulent flows, is it not? हाँ, पहले ही मौके पे किससे लिया. So we'll start with the correct answer. Super. 4612 is the right answer. Let us see question number 45 in gate 20. Yeah, question number 45. Yeah, 4600 to 4625 on the dot. Point 0.5 also you got? Super. So you are in the middle. Good. Now let us go with pipe flows, okay? Once you do it.
Sir, 4613, sir.
Very good. Very good. See, I'm fortunate that students with the without doing a topic only they will do the questions. Is it not? I've not done this. Is it not? And you're doing it by yourself. This is what is the thing about extrapolation. Whatever you know, based on that, you try to figure out what is there in the which is unknown, right? We know what is Nusselt number, so that's how it comes. Nusselt number, we can guess that Nusselt number is, what is the Nusselt number? H D by K. Instead of HL by K, it is HD by K. Exactly. L is not there. The length is given there. No, not you. Yeah. So the D, L are characteristic numbers. Characteristic numbers varies with what is the type of flow you are considering. Same like Reynolds number. Done? ಎಲ್ರಿಗೆ ಸಿಕ್ಕಿದ್ದಾದ್ರೆ ಮುಂದುವರಿ. Huh? No, 4600 to 4625. So you get 2 marks. Yes, please. 4594. Then you are wrong. You've done mistakes. You should not use that you're using that calculator. Fine. I'm sorry. You should use the gate calculator always. Keep in mind. Very good. Super. So heat transfer is not difficult. Don't leave it. It's very easy. Is it not? See, any things becomes easy only after you do it a number of times. Even probability is easy, but sometimes we do not remember that. That is the reason it looks difficult. But tomorrow it will become easy. Got everyone? Now let us go with uh, the internal force. Okay, this is the next one. Internal forced convection. Let us look at it. We start half an hour only till 45. We are going. Okay, it's okay. So let us go with internal forced convection. Internal forced convection. Okay. So internal means it's going inside a duct generally. Duct can be circular or otherwise. Okay. So let us see. Now generally what happens is if you consider a duct, it can be a. Done? Can we go further? Done? Okay. So it's very important. Some small concepts are there which is useful even in our fluid mechanics also, which we have done already. We are just repeating. Okay. Now there is something called, see, when you have a duct like this. This is a duct. Okay, which you see AC ducts behind outside our outside when you come up, you can see in that Deepa Arcade, Enclave, is it not? Deepa Enclave, what is that called? Here, this Divya Enclave, Deepa Comforts, okay? Behind that, you can see those AC ducts, is it not? That, how is the heat transfer in those things, okay? Or maybe you're behind the air conditioner, you see those ducts, is it not? Where there is heat exchangers, any heat exchangers, shell and tube heat exchangers, or you can consider any heat exchangers for that matter. Their flow happens. There we have to understand how, see, what are the main point in all these flows, in the duct flows, what are the main points? Can you tell me? What are the design considerations in duct flows? What are the design considerations? One is heat transfer, right? So design consideration mainly, this is one of the things which is very important in industry. Okay, so in internal flows, The major design consideration is the major design considerations are, first one is heat transfer. Of course, yes, heat transfer, either making the heat transfer or stopping the heat transfer. If you see AC ducts, it has to be designed in such a way that it has to stop heat transfer. Or maybe in our when we go with this steam power plants, there it is also duct flow. In the steam power plant, from the place where boiler is there, from the boiler we are going to the turbine. When it goes from the boiler to the turbine, the steam loses heat, is it not? That losing of heat, that losing of heat should be stopped. So there are two considerations: heat transfer. You can either improve, or restrict, or stop. If you can, we should stop heat transfer, right? Which is very difficult, but still stop. Okay. Second one is pressure drop. Pressure drop is a major consideration. So whenever you have to, in the heat exchangers, generally it is a main thing which we have to discuss is pressure drop. Okay, so it's always the thing between pressure drop and heat transfer. So what is the pumping power which is required? For example, if you see about milk processing, in milk processing, one of the major thing in milk processing, what has to happen is the milk is heated up. Then before packaging, it has to be cooled. Okay, so they use something called plate heat exchangers. What do they use? They use plate heat exchangers. These plate heat exchangers are also used in distilleries. In distilleries, no, yeah, Gadang. Okay, in distilleries, they use these plate heat exchangers. Okay, no, not Gadang. It is pure distilleries. Okay, this is local. No, that is really good distilleries. You use that. You use plate heat exchangers. What are plate heat exchangers? You have plates like this, okay, which has a hole here, a hole here, okay, and a lot of plates are combined together such a way that alternate. Have you seen that? Yes. Deja vu. Understand? You know what happened? I'll continue. Okay, so here sometimes there are projections onto this. Okay, there are projection onto this. Okay, so that there are a lot of plates which are put together like this. Okay, there are series of plates. Okay, in one gap, one fluid goes, on the other gap other fluid goes. Okay, so if the fluid goes from here, it goes out from here, and then it enters over here. You understand? So this is the middle one, middle one. It does not go into this slot, it goes to this slot. So one is heating fluid, one is cooling fluid. Cooling fluid can be vapors. You understand? So heating fluid goes to one slot like this, and then it skips one, and then goes to the other. In between, the other one goes alternate. So what happens? These are all called compact heat exchangers. Very compact heat exchangers. You have a heavy surface area for the lowest. What do you say? You have high surface area for very small volumes. Okay, so these kind of things, but that these are also internal flows. Keep in mind, these are not external flows. So here, how to do it? It's complicated. We have to solve Navier-Stokes equation. We have to go with CFD along with energy equation. So the energy equation along with Navier-Stokes equation has to be solved. But that is not not the energy equation. We have gone here, not this equation. It looks really, really difficult here, this one only. But then you should not solve this. You are actually solving this one. That is what is all CFD is all about. So importance of CFD comes here only. But this convection diffusion equation is very easy to solve in CFD. The most difficult one is this part. Why is that a difficult part? It is difficult part because there is how to say, there is called non-linear differential equation. This is a non-linear part of the differential equation. Whereas if you consider this, is it non-linear? No, it is linear. So solving linear differential equation is easier, however difficult it is. Numerically, at least you can solve linear differential equation. Non-linear, never. That is why this is difficult, this is easy. Okay. So first when you take Malashekara and you start coding, Malashekara Bedagandu, that is one of the good book of CFD. Another one, Suhas Patankar is another good book. Okay. You have another one, Anderson, which is also a good book. Okay. But I like Malashekara. Suhas Patankar I have not seen, I have seen somewhere here, but it is considered to be a good book. Now, when these things are there, when you say, yeah, anyhow, so these are all internal flows. That's what I wanted to say. Okay, what happens, when you are solving these problems, you should get a perspective of where it is used. Questions are very less in here, and the questions what are there is like this one. So today, tomorrow morning, I'm going to complete internal flows, and on on from by Thursday, okay, Thursday evening, okay, I'm going to complete internal force. Then one more which is remaining is um, our natural convection, which I'll take one more class. That's it. One class for natural convection, then done. Okay, maybe one and a half like that. Okay, then we will go with radiation. Make sense? Okay. Chalo. Heat exchangers later. Yes, obviously. Then we will go with radiation. I did not say we are completing heat transfer. So then we will go with radiation. Then we will go with heat exchangers. Heat exchangers is also a small one. It does not take much time, but it may take around 5 to 6 hours. It is not like convection or the whole convection. How much hours will it take? That much heat exchangers will take. See, yesterday we started convection. Yesterday 3 hours. Okay. Today around 1.5 hours, 2 hours, 5 hours. Then another 5 hours we will take convection. Okay. That may be 6 or 7 hours. Okay. So now I hope you have written that down. Okay. Now some of the main things which is important here is two things. Okay. Write this down. Write this down. Nothing there. Don't have to write this one. You write. Okay. Rate detection is also if you want you can. Okay. Some people say that in mechanical engineers don't need coding. We had heat exchanger design subject, okay, in IIT. Okay, so our assignment was developing a code. It is for 30 marks out of 100. You have to develop a code to solve a heat exchanger problem. People who said coding is not required with the software interface, you have to do that. We had to do the this one, what do you say, what do you call that, GUI design, graphics user interface. You have to design that. It's not difficult. You think it is difficult. It's not. Okay. Internet is there. Huh?
How much time did you?
We took around, see, it is for the whole semester it was. Okay. But then the amount of time we took was last minute only. Last 2 or 3 weeks, we struggled like it before the submission of assignment. That was going in our mind. It was planning actually. It was like bamboo, to say Chinese bamboo tree. When you give an assignment, see, I have to give one paper now. Look, the last date is December 31st. Okay, so I'm starting. I'm planning now. It's like I'm building the route, and at once On December 30th, the whole paper will be ready. Fantastically ready. Understand? That is what is called Chinese bamboo tree. That Chinese bamboo tree, you know, right? You put it for 5 years, you put a sapling, you won't see anything. It's just roots. You put water continuously, nothing is seen. Okay? And after 5 years, a small shoot starts. Within 1 week, it would have grown to 60 feet. You know this? This is called Chinese bamboo tree. Till then, it would have developed the roots. You understand? And at once, it develops later on the. No, it is not a proper reason. It is to say that for the entrepreneurs, it is not to be used in this context. It is to be used for entrepreneurs to say that first develop your strengths. Once you develop your strengths, you can grow later. Same thing I say to you people also. Now you are also Chinese bamboo trees. You have to put the same efforts. Now it might not see till 25, 26, nothing is seen. But then one break, you see the way you grow. It's huge growth. I've seen people. Like I see my own friend, okay, who is Hari Ganesh in IIT Madras. Okay. Yeah. He got into MATLAB, is it not? Yeah. Or tell me, you said something. I could hear it. Okay, but I don't want to comment on it. It's a different case. Chalo, let us go further. Now let us go with average velocity and temperature. Average velocity and temperature. This is very important. Average velocity and temperature. Okay. So generally, what happens, what is Q? What is the flow rate in a pipe? Flow rate in a duct can be given as Q dot is equal to integration of integration of rho u of r, u which is a function of radius, into d of that small radial area. Is it not? Radial area can be anyhow. Okay. Now this can also be equal to rho v average divided by the total area of cross section. So what we can write, v average, that is the average velocity, can be written as integration along the whole cross section AC into rho into u of r, means the velocity is different at different r, is it not, into DAR divided by rho into AC. That would be my, in general, the average velocity. This you write it as 1. Okay. Next, another thing. Also for a duct, for a circular duct, for a circular duct, this V average, this V average for circular duct can be written as 0 to R. I can write rho U of R into 2 pi R dr divided by rho pi R square, correct? This becomes equal to 2 by R square integration of 0 to R into U of R into R dr. Very important. Correct? U of R into R dr. Pi pi cancels, 2 comes here. Make sense? Clear? So what happens? V average is this. This you write it as equation number 2. Important. Both are important. Similar to average velocity, there is something called average temperature. Let us look at it. Okay, it's already time. Okay, We have just started.
Take 10 more.
10 more minutes will take. So 5 minutes break is enough. Okay, fine. So, okay. So that's better. Okay. So write it down. Then we will go with temperature. Take curve. Done. Okay. Next. Huh? Clear? No? Okay, next. Next thing is uh, we will go with average mean temperature. See, when a fluid is going in a duct, say this is a duct here, okay, and the fluid is moving in the duct, we know the temperature variation is also there in the duct. What is the temperature variation? We do not know, right? So it may be so that you may have actual temperature difference, maybe something like this. If it is a cold fluid which is moving, okay, in the hot pipe or the hot surrounding, then what may happen? You may get like this, the velocity profile being, not the velocity profile, the temperature profile being like this, with maximum at the corners and the minimum at the middle, right? Or it may be, if this is a duct, okay, this is a duct. So you have to keep in mind it is like a, to say, it's a surface, it's not a line. So you have to understand it's a surface, it's a cup surface, okay? And then if you consider other way around, it is hot fluid moving and a cold this moving. So it may be in this way also. If this is a duct, this is a temperature. So it may go like this. Understand? So it is not zero, velocity is only zero, temperature is not zero. So you may have a T max, right? You may have a T max, and then this is T wall, very important to write. This is T wall, and this is T max. Now this, if I say, is equal to this, if I write it, these are all actual case. These are actual cases. Actual case 1, this is actual case 2.
The second case is for what, sir?
This is hot fluid, cold wall. First one is cold fluid, hot wall. So this is the case for cold fluid, hot wall. This is the case for cold wall and hot fluid. Winter is coming. Winter has come. Is it? Okay. So, I was continuously in that Game of Thrones. I don't know winter has come or not. Next, have you seen Game of Thrones? I don't know. Game of Thrones, yes. No? Huh? ಇದು temperature variation ಅಪ್ಪ. Temperature variation. Yes, in a flow. It's a pipe. What is that we are doing? We are doing internal convection, is it not? What happened? What is the thing?
You heard it as filter. What is
Huh?
filter? You heard it as filter. What is winter is coming?
Ah.
Winter as filter.
Winter has filter. Okay, I don't know.
What filter is?
No, I did not say winter has filter. I
No,
said,
you heard it as filter.
okay. Chalo, don't worry. So, cold fluid, hot wall, and cold wall, hot fluid. These are the two things which can happen, and these are temperature distributions. Those are temperature distributions which are there. Make sense?
Basically, that the wall is spotted.
Cold, yes, cold fluid, hot wall, cold wall, hot fluid. That's it. And this is temperature distribution. But now, see, just like our in average velocity, we think, see, in the average velocity, when you consider the actual velocity is parabolic. but you consider average velocity. When you consider average velocity, it's similar to temperature, average temperature. So you may have a average temperature. This is idealized. This is called average mean temperature. This is called average mean temperature. This is called average mean temperature in the duct. Okay, it may not be circular also. Okay, so this is idealization of duct flows. Temperature of the fluid in the duct flows. Temperature of fluid in the duct flow. Let us look at it how it comes. So what should happen? Just like Q is there in our uh, the Q is the flow rate. Okay, volume flow rate is there in pipe flows. Here we have energy flow rate. So energy flow rate of the fluid. So we have to keep in mind it can be air or gas or liquid, both are there. Okay, so it is energy flow rate of the fluid of the fluid is equal to m dot cp into t mean. This is called t mean. M dot cp into t mean is actually, I think civil engineering class is open. Yeah. I'm taking classes for them. Okay. Anyhow, chalo, don't worry. Okay. So people came and went. Okay, thinking that I'm doing classes for them. Okay, and maybe they have thought that it is not 7 o'clock. Their class starts. Vail Murugan sir's class starts. Okay. So m dot cp into tm is actually equal to integration along the whole m dot, whole mass flow rate into cp into tr of m dot mass flow rate, which is actually equal to integration along the area of cross section, each mass flow rate. This is delta m dot. I'm sorry, delta m dot. Each mass flow rate delta m dot is given as rho cp. I can write tr u of r into DAC. Very important, students. This is the energy flow rate. This is the energy flow rate. Now what we have to write? M dot Cp, is it not? So we have to divide this by M dot Cp. We get Tm, T mean. I hope you understand. Delta M dot is rho into UR into DAC. Correct? No? Getting the point? I'll repeat that tomorrow again. This mean temperature is very important. And with respect to this mean temperature only, we see everything. Okay. It is also called bulk mean fluid temperature. That is, you take the whole fluid as a one bulk. So it is called bulk mean fluid temperature. That's how also it is called. Okay. So fine. Next. Next question is this. Okay. Next topic is, see now what next what we have to do? We have to find Tm. What is Tm? Have a have a view on the number. To say time, students. So another 4 minutes remaining. I will write that. That's enough. Okay. I'll write Tm. That's what happened. Correct. No, I have to look at the time also. And once Murli sir comes, he will be continuous, right? Okay. Okay, one TM I'll write, then it's done. Okay. So TM is equal to, I always see that it is both way, that is TM, that we'll discuss later on. Okay, it is equal to integration of m dot Cp Tr of delta m dot divided by m dot Cp. Correct? No, this is integration. Okay. integration of m dot, okay, or I can write Tm is equal to integration of 0 to r for duct flows or circular ducts. Okay, I can write Cp into T of r into rho u of r into 2 pi r dr, correct, divided by m dot is what, rho v average, velocity average, into pi r square into Cp. This together will come as 2 by 2, here it comes out 2 by V average into R square into integration of 0 to R, T of R, U of R into RdR. This is the mean temperature. This is the mean temperature. So to evaluate, instead of having all the changes, we can consider the whole fluid to be at the mean temperature. So we'll stop it here, students. Still more we have to do. This is also called bulk mean fluid temperature. This is also called bulk, no, wait. Not this. This is the mean temperature. Okay. I will tell you what is bulk mean tomorrow. Okay. We will explain that tomorrow. Okay. Then we will go with different, will not derive, okay, but we will just give the numbers, and we will talk about entry length, okay, hydrodynamic entry length, thermal entry length, okay, and two cases, constant wall temperature and constant heat flux. These are the two conditions in which pipe flows has to be analyzed. Okay, let us do it. Okay, thank you, students. So we'll meet again with